Hi, thank you for returning. I'm a little sick, so I'll try to speak up, but if you do not hear or cannot read, please let me know. So the goal today will be to talk more about electric networks and to prove, for instance, yes? You cannot hear? Okay. So the goal today will be to prove that Z2, the cubic graph, is recurrent. Who has seen this fact or know how to prove it? Yeah. No one has seen this fact. Okay. Right. The classical proof due to Polya, perhaps you know how it goes. You look at what is the probability that you return to where you started after n steps, and you show via Stirling's estimates that this scales like a constant over n. And just because this sequence is not summable, it follows that you are recurrent, that you return to where you started infinitely often. But what if, so we will prove that, but we'll prove something a little stronger. What if you take Z2 and you remove a single edge? Right? Then your proof doesn't work, because there's always the possibility that you are at this one vertex that doesn't have an edge going there, and it just doesn't work. But of course, it should be obvious to anyone that Z2 without an edge is also recurrent. But I do not know of any direct proof of this fact without going to electric networks. So this is a strange thing. And in fact, there's a general statement that is also very obvious to obvious intuitively, that if you have a recurrent graph in which the simple random walk always returns to where it started, then any subgraph of it is also recurrent. Right? This is also very intuitively true, but how do you prove it without the theory that I'm about to show you, that perhaps you know, is unclear to me. And I don't know if you have any direct way of showing it. I will be very happy to see it. So just a reminder what we defined, right? We have G that is a network, right? A graph, a finite graph with two distinct vertices, and we defined right, A and Z are source and sinks, and we said that H, which is a function from the vertices to R, is a voltage. Just to remind you, is a voltage if it is harmonic on all the vertices except A and Z. And I guess perhaps I didn't say it last time, but I guess it's I don't want to consider the constant function, so I'll also assume that H of A is different than H of Z. Okay? So this is something we understand fairly well, and we want to talk about the dual concept. So this is a voltage, and the dual concept, when you talk about electricity, is you have a voltage and you have a current induced by this voltage. So to talk about currents, we need to talk about flows, right? So we already define what a flow is, flows and currents. Right? So a flow, as we said, the flow theta is a function from directed edges of your graph to the real numbers. So I'll call this set the E with an arrow above it, the directed edges of the graph. Directed edges. A flow, and when I say a flow, I always need to say a flow from where to where. So it's always, in this case, it's always going to be a flow from A to Z. There will be some cases where I'll have flows that don't have a sink or don't have a source. But when you have a finite network, we have a source and sink, and it has to satisfy one. It has to be antisymmetric, as we said. Theta of xy is theta of yx. Minus theta of yx? Question? No? Just lifting the pen. Okay. And secondly, for every vertex that is not A and Z, the flow coming into the vertex equals the flow coming out of the vertex. 2, for any x, for any vertex that is not in A or Z, the sum of the flow xy, and this is sum over all the neighbors of x, of the flow from x to y is 0. So this is one way of writing the flow coming in equals the flow coming out. And of course, if you have, this is all linear equalities, right? So if you have two flows, you can add them, you can multiply them by something, and you get, you remain within the class of flows. So there's one, if you have a voltage, there's one special way of getting a flow, right? And what is that? You look at the differences of the voltage across the edge, right? So, so this is a definition. Given a voltage, right, we say that the current flow induced by H or associated by H, whatever you want, current flow induced by H is, so it's theta. I should write theta H because it depends on H, but I'm not going to do that. So theta of xy in this direction, right, is the conductance on that edge times h of y minus h of x. Right, so this is the flow, and it's obviously antisymmetric, right? And we only need to check, to be convinced that it's a flow, we need to check the second condition. And the second condition, the fact that the flow coming in equals to the flow coming out, follows from harmonicity. So let's verify. So 1 is immediate, of course. So let's verify 2. Right. So I have a vertex x, right? Or if I look at the sum of all the neighbors of x of theta xy, right? I just use this formula. So what I have here is the sum over, use the formula and open the parentheses. I have here the sum over the neighbors of x, sum of y, of c x y h y, right? Minus the sum over y, c x y h of x, right? And you remember that harmonicity was the condition that if you take this sum and divide by pi over x, you get the value of h of x, right? H of x is the average of its neighbors, right? So this thing equals pi x h of x, right? And this thing, h of x, of course, does not depend on y. You take it out, and this sum is just defined to be pi of x, right? So this is also pi of x h of x, and this is 0. Okay, so this is indeed a flow. So the first thing you may ask yourself, is there some sort of bijection between flows and voltages? And the answer is not just like this, because you can have, there are more flows than voltages, but flows that come from voltages, current flows, satisfy another axiom of electricity that we like to think of it, and this is called the cycle law. Right, so we think about a current. A current does not waste energy, right? It will not go in a circle in order to get from A to Z. It would prefer not to go on that circle and go directly to Z. And we can see this, and this holds for any flow that is obtained via a voltage, right? So a current flow. Question? No. So note that a current flow satisfies what is known as Kirchhoff's cycle law. Right? What does it mean? It means that for any directed cycle in your network, right? Again, the network is undirected, but we always think about having each edge there with both directions, right? So for any cycle, E1, I'm writing this directed, EM, right? Just E1, E2, E3, EM, right? If I add the values of the flow along this cycle and multiply by, I need to cancel this term, so I multiply by the resistance over xy. So the sum over I from 1 to m of r x y h of r of ei times theta of ei in this direction, it is 0. Right? The resistance does not depend on the direction, so I didn't put the arrow above it. And and theta, of course, does depend on the direction, so it's important we go on the cycle in the right orientation. Can you see? Is my handwriting large enough? Yes? Good. Not so much? I'll try to write a little bigger. So this obviously holds just because of the definition, right? When you have a cycle, this sum is telescoping. It starts where it ended, right? So it is 0. So now the question you can ask yourself: if I look at all the flows that satisfy essentially 3 axioms, 1, 2, and 3, let's call it 3. Is there some sort of bijection between that and voltages? And now the answer is yes. Every flow that satisfies the cycle law corresponds to some voltage. Okay, so this let's observe this. Right, so and once we have this, we have a complete characterization of voltages and current flows. Okay, so so let's write this as a claim. This is very easy to prove. Nothing was so difficult here. So given a flow satisfying, okay, sorry, I promised I will write larger, satisfying cycle law, right? Then the assertion is that there exists a voltage H on the network such that, let's call this star, right? Such that the voltages you get from the differences of H on the differences of H times the conductance on the corresponding edge, right? By the way, if you look at this formula, this is a manifestation of what we call in high school Ohm's law, right? The current is proportional to the voltage difference times the inverse of the resistance, right? Or right, and this is over one particular edge, right? And our goal is to show that this thing holds, or define it in a way so that it holds over all the network, over between A and Z, right? So this is where we're headed. So given a voltage H, there exists a voltage such that star holds. Is this voltage unique? Up to an additive constant, right? Of course, I can take this voltage, add the number 5 to all the values, and star will still hold because I only look at the differences, right? And it turns out that this is indeed unique. H is unique up to additive constant. So how do you, if I'm giving you a flow that has the cycle law, how do you define the voltage? Right, I'm given a value, I'm giving a vertex x, and I want to tell, and I want to know what is h of x. What do you do? Balint? I'm joking. Yeah. Right, you take a path from the root, say from a to x, and you sum the values of the differences, right, over that path. And because of the cycle law, right, it doesn't matter which path you took. So this is well defined, right? So let's write this down briefly. So, right, it's very easy to check all these things, just combinatorially, right? So for every x, for a vertex x, right, let you take a directed path from A to X. So let's let E1 up to EM, it's not a cycle this time, be a path from A to X. Right, so it's a directed path. Yes, question?
I am a little confused. So what is exactly R?
Oh, sorry. This was from R of E is the reciprocal of the conductance. Okay. Any other questions? Again, please feel free. I can barely see what goes on here. So perhaps I'll just define h of A to be 0, right? I can always fix one point and give it a value, right? And I'll define h of x just to be the sum from I from 1 to m of r ei theta of ei, right? In the right direction. Right? So this is the value of x, and of course now we need to check that it's a voltage, and the reason that it's a voltage is simply it simply follows because so firstly this is well defined because of the cycle law, right? Otherwise this doesn't make any sense. Well defined due to the cycle law, right? Because of course if I take two paths leading to the same vertex, that means that they have to have the same value, right? Because if you attach these two paths together, you get a cycle from A to Z, right? And it follows that it has to have the sum over the cycle is 0, meaning that the two values had to be the same. And why is this harmonic at each point? Well, right, I want to look at hy minus h of x, right? Let's look at the difference of hy minus h of x. Because I have the choice of any path, to compute h of x, I could take one path, right? And then to compute h of y, I take the same path and add the edge xy to it in the direction from x to y. And the difference between these two is just what the flow on the edge xy times its resistance, right? So this will just equal rxy times the flow on xy, right? And when you sum this over y with appropriate normalization, right, you get exactly the equation defining harmonicity of H. So this is indeed a voltage, and I'll leave you to convince yourself that uniqueness holds as well. This is just easy. It follows from uniqueness of the voltages. Okay, so I'll leave you as an exercise uniqueness. Exercise in the realm of you can solve it while you're drinking coffee and smoking a cigarette outside for 5 minutes or less. And no need to write anything. Okay, so this is this proves the statement. And now let's just mention one other concept, which is the strength of a flow, right? If I have a flow from A to Z, right, the mass going into the amount of water going into every vertex equals the amount of water going outside of this vertex, except for the two vertices A and Z, right? And we think about from A, I'm putting a liter of water, and a liter of water is coming into Z, right? So this quantity, this liter, which is whatever it is, could be half a liter, is what we call the strength of the flow. How much water or electricity is going through that flow? So the definition is just, if I'm given the flow, the strength of theta, of flow theta, is, and we use the notation, perhaps a bit misleading notation like a norm. It's just the amount of things, right, coming out of the initial vertex A. So I'm summing over all vertices adjacent to A of theta AX. right, in this in this direction. Right, and obviously, when I look, so you have to convince yourself of the fact that this is easy. Again, another thing to compute while you're having a cigarette is that the mass going into z is exactly the same thing, right? So this one I will write if I sum over all the y's such that y is adjacent to z, but this time instead of ax, I'm going to write xz, right? So theta yz, right? This also equals the strength, right? This completely intuitive, and of course it follows immediately by the axioms. Okay, so we still want to show that our goal is to show that there is a bijection between voltages and current flows, or flows that satisfy the cycle law, and this will follow immediately once we show that if we have two flows, right, that satisfy the cycle flow, that satisfy the cycle law, right? Of course, they don't have to be the same because they could have different strength, for instance. If they have different strength, they're obviously not the same, but the statement is if they have the same strength, they have to be the same flow, right? So this is the assertion, right? So the claim, right, and I should perhaps mention that all of this has a continuous counterpart that I'm not going to talk about because you need some more abstract nonsense, but it's not very difficult. So if theta 1 and theta 2 are satisfy, so again, they are flows from A to Z, and they satisfy the cycle law, and their strength is the same, right, then they are equal on all edges, right? And so the reason for this, right, and this tells us that that essentially the flows that satisfy the cycle flow, they are unique up to knowing exactly what the strength is, right? Because I could take one flow and multiply it by any number, and this I get the whole space of flows that satisfy this, right, is essentially, right, a one-dimensional space. Right? It's just multiplying by a constant. So of course, what I'm going to do, if I have two of these, I'm going to subtract them, right, and get a flow that has strength 0, and that I want to show has to be the constant flow, right, or the zero flow. Sorry, the zero flow, not the constant flow, right? The constant flow means that the voltages are actually changing, right? If the constant is not 0, right? So it has to be the zero flow. Reason the strength. So let's consider. So we just need to check, right, that if we have a flow that satisfies the cycle law. So consider theta to be theta 1 minus theta 2. This also satisfies the cycle law because the cycle law is also, not sure where, I've already erased it, but it's also just a linear equation, right? So you subtract two of them and you get also something that satisfies the cycle law, right? The strength is also linear in the flow itself, so you get that this, so this is a flow that has 0, the cycle law is 0, and now we only need to check, so we know that if we have a flow that satisfies the cycle law, it corresponds to some voltage. And our goal is to check that this voltage has to be constant. Right? If we do that, then you agree, I agree, that we are done. So let's do that. So let H be the voltage induced by theta. Right, and we have to check, so let's just see, so we know that H is harmonic at all the vertices except A and Z. So let's prove that it's also harmonic at A, right, and also harmonic in Z, and then we'll conclude that H has to be the constant voltage. Okay, so let's see, so we'll see, so let's check H of A. So I want to look at the average of the neighbors of A of the value of the voltage multiplied by the conductance, right? So so we need to prove that 1 over pi a of the sum over all the neighbors of a of h of x. We want to prove that this equals h of a. So we'll just put things in the right way. What is this? What is this thing? This is the voltage induced by theta, right? So when we look, so we had here, we know that right. We know that this holds, right? So I can always write this as right. This is and I forgot here. Right here, I'm missing the conductance, CAX. Right? This is the, if we prove that this equals h of a, then it is then h is also harmonic at a. Right? So and this will follow just because the strength is 0. So this is an immediate thing to check. This is 1 over pi of a, the sum over the same x's of CAX, and here I'm going to write h of a plus the resistance on AX of H of X. Sorry, of theta of AX. Right, because theta of AX, right, is, if the voltage is induced by theta, then theta of AX is exactly H of X minus H of A times the conductance, right? So conductance on the edge AX, so conductance cancels this. I have H of X minus H of A, so this equals exactly H of A. Right, let's continue over here, and or let's just do this without writing, right? So what we have, so we open the parentheses, and you see that what we have here is just H of A, right? Because the sum over X does not depend on A, so it gives me pi of A, and when I sum over X this thing, right, I get exactly, what do I get? Right, I sum, what do I get here?
So the resistance will cancel the conductance,
right? The resistance will cancel the conductance, thank you, right? And I still have the pi over A, and then I sum theta AX over X, so that gives me exactly the strength, which is 0. Right, and so I get that only this term remains, so this equals H of A. Right, so the voltage is harmonic at A, and you do the same thing for Z, and it's the same calculation, so you get that H has to be, H is harmonic everywhere, so H is constant. Right, if H is constant, then that means that the original flow was 0, right, just gave 0 to all the edges, and that means that theta 1 equals theta 2. Right? Is everyone happy with this? Or let's ask it this way. Who is unhappy with this proof? Who is unhappy generally? No one. Find it hard to believe, but never mind. Okay, so now we're finally, after we've settled all this, we're in a position to define what is the resistance of the network, the resistance between A and Z of the entire network, not just of an edge. And we call this, this term is called the effective resistance of the network. Right, so the definition, so firstly we claim, so this is a corollary of all this, a corollary, right, for any voltage, for any, for any voltage H and the corresponding and the induced current flow theta, or perhaps I should write theta of H, the voltage difference H of Z minus H of A divided by the strength is a constant that does not depend on the choice of the voltage, right? Does not depend on H. Right, and the reason is exactly because we have a one-dimensional space, right? There's just one-dimensional space of such voltages, given that is determined only by the voltage difference, right? I set the voltage difference to be something. There's just one such value, and this is normalized exactly by the strength, right? Because the strength is again just a linear thing. You multiply by the same number, you get, so the ratio cancels, right? So this is just a number that is associated with the network, right? And depends, of course, on A and Z, but it does not depend on anything else, right? You just look at the network with the resistances and conductances, and you have this number. So this number we will call, and of course this number is the voltage differences of the network divided by the current flowing through this network. So of course it's very, due to what we think of as Ohm's law, this is very natural to call this the resistance of the network between A and Z. The common nomenclature is, we call this the effective resistance. Effective resistance between A and Z. And this will be a very important number that we will discuss throughout this course. We'll see all sorts of ways of estimating it, and most importantly, because we built it from harmonic functions that we know that we built from random walks, we understand that this should have some very deep, or not so deep, even easy, probabilistic interpretation, right? So let's firstly say what is the notation that we write. So we always write, and this I'm writing because we'll use a lot, so perhaps I'll even write it big. We write effective resistance, right, from A to Z. Right, so this is how I will denote this number, and sometimes it will be important to state on which network you're working on, so I'll perhaps write a semicolon and say the word G or something like that, but it should always be clear that there's some, just this notation, there's something missing, right? There's always a network on the background, and so for this to be well defined. Okay, so this is the effective resistance. What is the? Perhaps let's see just one or two examples of how you would compute it. So let's look at the one particular graph just so we'll be on the same at the same side, right? Let's look at this graph with three edges. These are A and Z. I'm sorry for the absolute trivial examples that I give, and the reason that the examples are trivial is that it's usually hard. It's usually not easy to compute the resistance precisely, unless this is you see something simple like that. But it's more common to estimate it up to constants or whatever. So here's our graph. What would be the resistance from A to Z? If I don't write nothing on the graph, then I mean that the edge resistances are units. They're one. So the resistance will be 3, right? Just by intuition. So let's prove this formally. I need to compute the voltage on this graph. So I'll find a harmonic function. I'll give the value 0 here, 1 here, 2 here, and 3 here. Right? Each value 1 is the average of 0 and 2. 2 is the average of 3 and 1. So this is indeed a voltage. The voltage difference is 3, and the strength coming out of A is just 1, right? Because the voltage difference along this edge is 1, so we get 3. Right? Another example is, of course, let's look at this graph. Right? What will be the resistance here between A and Z? Just intuitively. 1, right? Let's prove it. So I'll find a harmonic function. I'll put here 0 and here 1. And so this value needs to be the average of these 3. I'll put here a half and here a half. You can see that by symmetry, these two vertices have to have the same voltage, right? The voltage here is the probability that I hit Z before I hit A. Right? So by symmetry, right, these have to have the same voltage. So now this is an honest-to-God voltage. The amount of the voltage difference is 1, right? 1 minus 0. And the amount of flow coming out of the original vertex is half plus a half. That's also 1. So it is 1. Right? Another thing that we could see that there is some sort of manifestation of what we call the parallel or series law, right? That we will talk about in a second. Okay, so let's talk about what is the probabilistic interpretation of this number, right? What is this number? So this is going to be a claim or a definition. So let's first define. So we had the stopping times that we call tau x, which is the first time that you visit x. I wanted to define just one more stopping time. So for any vertex in V, we'll define tau x plus to be the minimum positive time that the random walker xt visits little x. Okay, so this I'm reminding you big X t, or sometimes I write t, sometimes n. This is just the random walk. Right? So the claim is, and this is very easy to prove, but I think it's important to see that the effective resistance between A and Z is proportional to the inverse of the probability when you start from A and Z, to visit Z before you return to A. Right? So let's write down exactly also what is the proportion constant. So this is 1 over pi of A, right, times the probability when you start from A to visit Z before you return to A. So of course, you start from A. So if I didn't have this plus here, this probability will be 0. Right? But with this plus, then there is a probability that in the excursion from A to itself, I visit Z. Right? This is essentially what it is. Let's look that it satisfies. Right here, it obviously works. Pi of A is 1. The probability of when I start the random walker from A to visit Z before returning is exactly 1/3. We all know that from the gambler's ruin problem. And the resistance is 3. So it works out on this example. Clearly, it should be true for everything else. So let's prove this. And this is it's easy to prove once you have all this, because this is all these are all linear things. There's nothing too difficult. So let's take the h of voltage. Take h to be a voltage, and as usual, we can, since we understand that this is a one-dimensional space, right? We can just normalize the voltage to have voltage difference 1, and to take h of A to be 0 and h of Z to be 1. Right? Once we have this voltage, which we know exists in unique, the value at every point x is just the probability that I visit Z before I visit A. Right? So now we just now we just do what you would do, obviously, or just to continue in a straightforward manner. You look at this quantity, and you want to estimate it by conditioning on the first step of the random walk. Right? This thing is the sum over all the probability that I visit Z before A is just the sum over visiting Z before A of each of the neighbors of A times the probability that you move there. Right? This is just a one-step Markov property. So I look at PA, that I visit Z before A. Right? So this is just by complete probability, or however you call it. Right? This is just depends on when I move or where I moved. So this is x that is a neighbor of A. Even x there could be a loop in this graph. There's no problem, right? And then the value will be 0 of what I write here, but this is no problem. The probability that I moved there, which is CAX divided by pi A. Right? This is the probability that I moved on the first step from A to X. And then the probability starting from X that I visit Z before A. And this is exactly as we saw in the construction of the harmonic function. This is just h of x. Right? This is the value when I put 0 and 1 boundary conditions for the voltage. Right? So this is, this is it. So what we have, so I take the 1 over pi a, I'll put it outside. Right? So what I have written here is exactly, what is it? Right? I have CAX times h of x. Think about it. H of A is 0, so think about it this way.
It's the strength.
It's just the strength of the flow corresponding to this voltage. Right? So what I have here is just 1 over pi A, right, times the strength of the flow. Right? And we are done, right? Because the strength of the flow is just the voltage difference. Sorry, the strength of the flow is the voltage difference divided by the effective resistance, right? Just by our definition of what the effective resistance is. So this is 1 over the effective resistance. This is 1 over pi A effective resistance between A and Z. Right? So this number tells you, the most, this basic probabilistic intuition. And in fact, you could take this, all of these things, you could take this as the definition of the effective resistance and derive everything in the other way around, and it all works. And we'll see several ways of defining the effective resistance that are all equivalent and go the other way around. So some basic properties of this number is what we anticipate, from just considering these examples, right? I have this network that looks like this. I use what I know from high school as the series law, right? This will be equivalent to a network with one edge, right? On which the resistance is 3, right? So the conductance is 1/3 or 3, depending on what I prefer to write on this edge. And here, if I don't have this edge, right, then this will be, I will have here one edge from A to Z with resistance 2. Right? Because I'm adding in series, I add, and in parallel, I do something else. And in parallel, the reciprocals add, right? The conductances add in parallel, the resistances add in series. So I'll have here, let's write the edge resistances on the edges, because I prefer to think about resistances than conductances. So here I'll have 2 and 2, right? And right, so this is an equivalent, electrically equivalent network, meaning that the resistance between A and Z is the same. Right? If I have this as a chip, I could just replace it with this chip. And now the conductances here is 1/2 and 1/2, and they add in parallel. So the conductance is 1 of the resulting network. So I have a network that has resistance 1. Right? And I'm allowed to do this. So these are, I'm not going to state it formally. You can read the statement in the notes. I'm allowed to do this whenever I see such a sequences of edges. Now, of course, I need to make sure if I have 2 edges and I want to use the series law, I'm not allowed to have edges in here, right? Because this could obstruct the series law, right? So this vertex has to have degree 2. Right? And the same thing here. I have to have 2 parallel edges that I'm shrinking into, that I'm turning into 1. But what I am allowed to use, and this follows, is that I can use it on 2 different networks. So if I have, so this is just the series and parallel law for a few edges, right? But right, if I have let's look at the series law. Right, with no formal statement, just a drawing. If I have one network, which is A, right, to Z, let's call it Z1, and then from this vertex, I have another network from Z1 to Z, right, or let's call this a different name, just a vertex V, right? And this vertex is a bridge, so there are no edges from here to here. Right? This vertex, you remove it and you split it into 2 parts. Then you're allowed to say that the resistance between A and Z, right, equals the resistance between A and V plus the resistance between V, and Z. Right, so this is a kind of manipulation over a network that we will always do. Right? And similarly, you have what we know as the parallel law. Let's just say it because we're going to do this a lot. It's going to be a different drawing. I have a vertex A, and I have a network right here leading to a vertex Z. And then I have a network that is completely disjoint from this one that leads to the same, that ends at the same vertex. Right? And so the resistance, right, and I'll call this G1 and this G2. Right? So to calculate the resistance between A and Z in this union of these two networks, then the rule is that the reciprocals add. So 1 over the resistance between A and Z in G1. So here's an example where I do need to say exactly what is the network that I'm computing the resistance on. And I add the reciprocal of the resistance of the other network, AZ in G2. This equals 1 over the resistance in G1 union G2. All right. Is this clear? OK, so let's see perhaps let's see a quick example that shows, even though you already know it, that how would you do this? Just to show that the binary tree, for instance, is a transient graph, right? So let's do this again with just with a drawing. How would you do it without, so the usual proof that you can really estimate using the random walk estimate, you can really estimate the height that you are. But then perhaps this is not so robust. So if you have a tree like this, well, let's make it binary. Right, and this goes up to level n. Right, then you can start, and you want to see what is the probability, right, that you start at the vertex here. What is the probability that you reach height n before returning? So you could just use electricity to do that. So you notice that by symmetry of the tree, the voltages here, right? So now I want to treat all of the leaves of this graph as a single vertex and give them voltage. So here at the bottom, I'll put voltage 0, and here I'll put voltage 1 at all of the leaves, right? And by symmetry, all of these, the vertex, this vertex, and this vertex has the same voltage, right? It has the same number. The probability that when you start here that you visit the leaves before the root is the same, right? Just by symmetry. So I can glue these two things together, and this still is a network that is equivalent electrically, right? So this network will be equivalent to, this is the root A, and now I have two parallel edges here, right? And now I can glue all of these 4 vertices together because, again, they have the same voltages written on them. Every time I have a vertex with the same voltage, I could just glue it together and identify it to be the same vertex, right? Keeping all the edges, and everything remains the same, right? So you have to perhaps think why this is true. So here I will have 4 edges, and then 8 edges, 8, 4, 1, 2, sorry, etc. Right? So when I look at the resistance, the effective resistance from A to the leaves, so I haven't defined, by the way, what does it mean for electric resistance between a vertex and the set. But what I mean by that is that I take the network which I collapse all the vertices of the set to one vertex and collapse them and keeping all the edges together, right? Identifying them, gluing them, whatever word you want to use, and looking at this network and computing, now this set is one vertex, and I compute the ordinary effective resistance, right? So this effective resistance will be a half just by the, now I use the parallel law and then the series law. I get a half plus a quarter plus 1/8 and so on. So, and of course, this converges. So what I see just by the formula, right, we see that this probability of visiting the leaves at level n before returning to A is some constant, right, that doesn't depend that doesn't go to 0 as n goes to infinity. So no matter how big n is, you have some probability which you can compute exactly in terms of n just by computing this series. This series is already too difficult for me to compute, so I'll leave this to you. You can compute exactly this probability, and it converges. That means that in the infinite limit, right, you have some positive probability of escaping and never returning to the vertex A. Right? So this is a proof that the binary tree is recurrent. Okay, any questions so far? So this is the basic theory of electric networks, and you really cannot go a lot further. And you can see and you can already guess that this is all linear algebra in some form or another on a finite state space. So there's nothing very special here. So if you know that, you can also guess that you must earn something by looking at we haven't discussed here at all L2 theory, right? We haven't taken any inner products or something like that. So it must be, you have a feeling that you can observe this some in a different way just by considering sum of squares of something, right? And this is indeed a very useful thing for computing and estimating the effective resistance. And in the physics literature, when they talk about L2 theory, they call it energy, right? So this is what we'll discuss now, and this is really makes things very, very much more. You get much more powerful results by considering this L2 interpretation of electric networks. So let's discuss energy. Right, and our intuition is very clear, right? The current flow from A to Z, right, has to minimize the energy, right? The electric flow is efficient. Electricity is smarter than us, and it always chooses the best way of spreading the flow from A to Z. So we want to define what is an energy of a flow and not necessarily a current flow. So let's define that. The energy of a flow theta, a flow from A to Z, is just going to be the sum of squares of the flow across an edge, right, times the resistance. Right? So this is the definition, and it's also intuitive because energy, we have the feeling that some square should appear. And it's also intuitive that there should be a resistance there, because if you have a circuit with the resistance growing larger, then the flow needs more energy to go from here to there. So it's clear that at least the monotonicity will be in one way. So the energy of a flow, right? This is just this is the sum over all the edges of your network. The resistance over an edge, right, times the value of the flow over the edge. Of course, this depends on the direction of the flow, but we square it, so it does not depend on it anymore. Okay? So this functional is defined for any flow, right? Not only the current flow. So of course, what we anticipate is that the current flow minimizes the energy amongst all flows. But what do we have to take into account? Right, I can, of course, multiply a flow by 5, right, and the energy will grow by 25. Right? So I have to normalize. If I look at all flows of the same strength, then the current flow will be the one that minimizes the energy. Right? No one, at least from an intuitive level, no one could dispute such a thing. Or such an intuition. So let's prove it. This is called, in the physics literature, this is called Thomson's law. Thomson is the guy who thought about the electron for the first time. So this is Thomson law. Right, and let's state it and let's even prove it and discuss why it is an important thing. Right, so the resistance, so the Thomson law states that the theorem is that the resistance between two vertices in a network is the infimum over the energy of a flow, where theta is a flow from A to Z. Theta is a flow from A to Z, and it has strength 1. All right, so before we prove it, let's just discuss why is this a good thing. And the reason that this is a good thing is in most cases, when you are given some graph, some planar graph, whatever graph that you have, it's very hard to construct the current flow. It's hard to construct the voltage, right? This is exactly the quantities that we want to calculate. What is the probability when you're at a vertex that you visit this vertex Z before vertex A? This is what we want to estimate to begin with. So we don't know typically how to calculate the voltage, and we do not know how to calculate the current flow, right? The flow that you get from the voltage. But if you just have an idea of how to construct some general flow from A to Z, and there are many methods, right? This flow does not need to satisfy the cycle law. If you just, look at the graph and, I'll pick a certain flow that you can imagine, then this gives you compute its energy, and this gives you an upper bound on the resistance, right? And this will be our main tool to obtain upper bounds on the resistances just by building flows by all sorts of nice ways. So let's prove this just to make sure that we know what's going on. So the proof, let's first verify that this infimum is attained. So this infimum is indeed attained, and where would it be attained? On which flow? I said that. This is not a trick question, right? On the current flow of unit strength. Let's just do a sanity check. If I look at the unit flow of current strength, and I put the voltage to be 0 at A, what will be the voltage at Z? No. Sorry? The effective resistance, right? The voltage difference, right, divided by the strength equals the effective resistance. So it has to be this. This is two separate voltages that we look at. One that has 0 and the effective resistance on Z gives you the unit current flow with strength 1. And the other voltage that we're also familiar with is giving 0 to A and 1 to Z. And then the strength is going to be 1 over the resistance. Right? So this is just just that. So let's check, let I be. So firstly, let's check that this infimum is attained. So I is the unit current flow. By unit current flow, I mean that the strength is 1. Right? And let's compute its energy. Right? So the energy of I is, so perhaps here at the energy I could write this also, right? I count here each edge once, but I can also count it twice and divide by 2 if I count it in both ways. So this is 1/2 sum over all the directed edges, right, of R of E, theta of E square. Right, so what I have here is 1/2. And I want to sum over all directed edges, so I'm going to sum over all the vertices and then all of its neighbors, right? So I sum over every edge twice this way. So this is a sum over all the vertices x, all the neighbors of x, right? The energy is the resistance, R x y, times the value on that edge square, I x y square. Okay. So I somehow want to use the fact that this is a current flow, so that means that this was obtained from the voltage that receives 0 at one point at A, and as you said, the resistance on Z. Right? So I'm gonna take one term here, right? One of the things that I'm squaring, and I'm gonna write it as the difference of the voltage. So this is 1/2 times x sum over y, that is that is a neighbor of x. I leave the resistance as it is. Right, and one of the ixy I write as h of, should be h of y minus h of x divided by rxy, right, times the conductance. Right, and here I leave ixy as it is. So the resistance cancels. Right, that's that's one thing. And I now open the parentheses right here and write it again. So this will be 1/2 times the sum over x, the sum over y that is a neighbor of x, of hy times ixy, right, minus 1/2 the sum over x, sum over y that is a neighbor of x, of h minus, right, so h of x times I of xy. Okay? Is everyone, who does not agree so far? Or perhaps I should ask about your happiness level and just, okay, so let's look at the second sum, right, just to make sure. Whenever x is not a or z, right, we know that the flow coming into x equals the flow coming out of x. H of x does not depend on y, so when we sum over y this term, we get 0. Right? So the only terms that matter here are x equal a, right, and x equal z. What happens when x equal a? H of x is 0. Right? What happens when x equals z? Then h of z is 1. Right? Sorry. H of z is just h of z. It's going to be the resistance, right? And then the sum of things going into, so now x is z. So this is the sum of things from z to y, right? This is going to be minus 1, right? Because this is from z, sorry, from, so y is a neighbor, or is this going to be, it's going to be minus 1, right? From x is z, so this is from z to the outside, right? We know that z has 1 current going into it, so it's minus 1 current going out of it. So this whole thing equals plus 1/2 time h of z. Right? But what happens here, as you can guess, I will have the same thing. When x is when x equals a, right here I have, well, I actually don't have to do anything. I claim that it's exactly the same thing just by anti-symmetry, right? Because this I can write as minus I yx, right? And now you can observe that this is exactly the same sum, except that I changed the name of x and y. So this is, again, exactly 1/2 time h of z. So all of this is 1 time h of z. And by our normalization, that theta has strength 1, it follows that h of z has to be the resistance according to your claim. Right? So this equals the resistance from A to Z. Right? So indeed, the unit current flow gives you the resistance. Right? Its energy gives you the resistance, and now we have to claim that this is the minimal energy that you can obtain. Let's observe that as well. So I take any other, right? So let J be any other flow, be a flow, not necessarily a current flow. So the cycle law does not necessarily hold. And we look at but we do have that the strength is 1, because this is what we're minimizing on. And of course, we will write J equals I plus J minus I, right? And compute the energy this way, right? So the energy of J, right, is just the 1/2. Again, sum over x, sum over y, rxy. And perhaps I'll call J minus I, I'll call theta, just for convenience. What I have here is I of xy plus theta of xy squared. right? And I need to show you, what do I need to show you? So I open this parentheses, right? So when I take this one, I square, I get the energy of I, right? So this equals to the energy of I, right? When I take this square, and this one, I get the energy of theta, right? Plus the energy of theta, right? Which is also, of course, positive. The energy is always sum of non-negative numbers. So all I have to make sure is that the cross term is also positive, right? What is the cross term? The cross term is, there's a 2 that cancels the 1/2. So I have here a sum over x, sum over y that are neighbors of x, of theta xy times theta xy times I of xy, right? And this is, again, an easy calculation, right? Because now I'm going to replace, sorry? Oh, r, yes, I forgot the r. R of xy, thank you. Yes. And now, again, I write ixy as hy minus hx. I use the same voltage divided by rxy, right? So this will be just this last term that I want to show that is non-negative is just the sum over x, the sum over y of theta xy times I of y, h of y, thank you, h of y minus h of x. Okay? And now you open the parentheses, right? And you do the same thing. So let's just look at the term sum of x, sum of y, theta xy, h of x, right? When I sum over y, right, for every x that is not in the network, when I sum over y, this is the flow, so the sum is 0, right? For every x that is not a and z. But for every x when x equals a, then what I have written here is h of a times the sum over a y, right? But this theta had strength 0, right? So what you get there is 0. And this one you open, you see, you do the same thing with anti-symmetry, and you see that these are equal. So it's almost the same argument, and you get that all this is not just non-negative, it equals 0, right? So this thing equals 0, right? And the proof is done. Okay. So what is the advantage of all this? The advantage now is a statement that seems obvious to anyone who listens to it. If you have a network, right, with a certain, and you look at the resistance between A and Z, if you choose an edge and increase its resistance, then the total resistance between A and Z can only increase, right? So you have monotonicity, right? It's a very intuitive thing, but without this point of view of energy, I do not know how to prove it. So let's state this corollary. And this form of monotonicity is known as, at least in the physics literature, but also in the math, as Rayleigh's monotonicity. Rayleigh's monotonicity right? Let's even write it informally. You have the formal statement exactly in the notes. So increasing resistances, increasing edge resistances, right? On each particular edge, you increase the resistance. What you get is the effective resistance increases weakly, right? You can have an edge that no current goes on it, and then you can increase the resistance to as much as you want, but the effective resistance will not change, so this one cannot decrease. Right, and the reason is, why does it follow from this, is because you look at the resistance and the increased, right, in the network where you increased. You look at the unit current flow, right, the best flow that gives you the resistance, and now you take that flow on the previous network with lower resistances. Now it's not a current flow, right, but it's a flow that has an energy that is even smaller than what it was before. So the resistance on the previous, on the original network was smaller or equal, right? So it's there is wiggle. You take one flow, the electric flow on one network, and consider it on the old network just as not as an electric flow, but just as a flow, and apply Thomson's principle. And the same thing in the other way around. If you decrease the resistances, the effective resistances on your network cannot grow. Okay, so this is very nice. And in general, when we want to give upper bounds on resistances, we want to construct flows. How do we give lower bounds on resistances? By the way, does everyone see that now this implies that if Z2 is recurrent, then also any subgraph of Z2 is recurrent, right? Because you look at a big ball in Z2, right? And you calculate the resistance from the origin to the boundary of the ball, right? So if Z2 is recurrent, it means that this resistance goes to infinity, right? Because resistance going to infinity from a point, means just by our probabilistic interpretation that the probability starting from A of hitting the boundary of the ball before returning, right, goes to 0, right? So that means when we take a limit, the probability of escaping and never hitting the origin is 0, right, by continuity of probability measures. And now, if we know that if we remove a few edges, that we can think about that as increasing the resistance to infinity, right? This implies the resistance has only grown, right? So now the probability of hitting a big sphere before returning to A is only smaller, right? So we get this monotonicity, even though we still have not proved that Z2 is recurrent in itself, right? We need an argument saying that, but let's do that. How do we obtain lower bounds on resistances in a similar variational thing? So I'll leave this as a nice exercise. It's again not very difficult. Perhaps you'll need 2 cigarettes for this. So if you construct a flow, you get.
In parallel, or you?
It's up to you. Right, so if you construct a flow that has good energy, you get an upper bound on the resistance. And if you want to get a lower bound on the resistance, you have to construct a function that looks close to the harmonic function. So here is the statement. The exercise is so firstly the energy. So the energy now not of a flow but of a function. Energy of H function from V to R is just, I define it to be the sum over edges, right? E equals xy. This time I'll multiply by the conductance and not the resistance of H of x minus H of y square. You also know this is perhaps the Dirichlet energy of a function, and it's not very difficult to see from this, right, that that 1 over the resistance between A and Z is the infimum over all energies of functions, any function that assigns real values to the vertices, as long as so H is a function from V to R, as long as you normalize the boundary values to be 0 and 1. H of 0 is 1. H of A is 0, and H of Z is 1. And of course, what will be the function that minimizes the energy? Sorry? The voltage, the harmonic function with boundary values 0 and 1 is that. By the way, it's very easy to see that, right? Because if the energy is not minimal, right, and you have a point that is not the average of its neighbors, you could just give it a new number, the average of its neighbors, and obviously the energy drops at this. So it's obviously a function that minimizes this has to be harmonic. Okay, so so this is the basic energy point of view of electric networks. And let's briefly discuss what it means on infinite graphs, because this is what we're interested in. And it's already what I said. If you have an infinite graph, right, so given an infinite graph, this time an infinite connected graph, I want to define a quantity, and I have a vertex A. I want to define the quantity, the resistance from A to infinity. Right? And this, of course, can only mean one thing. I take some exhaustion of the graph by finite graphs that become larger and larger, and take the resistance from A to the boundary of these graphs and take a limit. Right? So given what is an exhaustive set, so let's let Gn, subgraphs of G that are finite, they're increasing, say, Gn is contained in Gn plus 1, and their union is all of G. Think about the union as a union of edges, right? And let Zn, what do I want? Zn is the boundary. So Zn be the gluing of G minus Gn. So I look at all the vertices that are outside a big ball, right? And I glue all of these into one vertex, Zn, and connect it, keep the edges that connect it to outside. For instance, if this was a big chunk of Z2, right, now I have Zn will be connected to all the boundary, and so forth. I didn't draw all the edges here, right? So everything outside of this box, this was G1, 2, 3, 4, or something like that, and I connect that. So what would be the definition? So the resistance from a vertex A to infinity, right, in G, right, in the infinite graph, is just going to be the limit of the resistance between A and Zn and all of these finite networks. Limit as n tends to infinity of the resistance between A and Zn. Why does this limit exist? Sorry? By monotonicity, but in which direction? Is this right? Sorry, it's increasing, right? It's increasing. These are not subgraphs of each other, right? In fact, they are, you glue parts of the original graph. So think about it for yourself that this is an increasing sequence. Well, it makes sense, right? If you have, right, think about it. If you have an infinite line, then right, this resistance could be infinity. But at G1 it will be 1, for G2 it will be 2, and so forth, right? So by the example, it has to be increasing. The monotonicity tells you that this is increasing, and also the monotonicity tells you that this doesn't depend on the choice of exhaustion. Right? Let's write this down. So this, so the note, this is increasing. Right? So the limit exists, but could be infinity, and does not depend on Gn. Right? Because if I have two such sequences, I can always kind of sandwich them together. Right? If I have one Gn, if I have Gn and Gn prime, for each Gn I can find a Gn prime that contains it, and so forth. So you get that one limit is smaller than the other, but it also works the other way around, so the limit have to exist. So this is just a number that depends on your infinite graph and perhaps the edge weights on it and your particular choice of vertex. And all the theory that we learned about energy and things like that just extends to this infinite case. So let's say what is the without a proof, let's just say what is Thomson's principle, right? So claim the effective resistance from A to infinity is henceforth the infimum over the energy of a flow. And now I think about a flow from A to infinity. What does that mean? I can just think of a flow that has a flow that for every vertex except for A has the node law. The flow coming in equals to the flow coming out, except from A. Right, so this works. So this is A. Theta is a flow from A to infinity. Right? And I just told you what it is. And the strength, the amount of flow coming out of A, is 1. Right? So this infimum is well defined. Of course, it could be infinite. If the graph is recurrent, then this infimum is infinite. There's no way to construct a flow that will have a finite energy. And this, of course, all follows from the finite theory by taking these limits, and that's it. So let's write down the corollary of how do we distinguish, how do we find if a graph is transient or recurrent, just by electric theory. Right? The following, so G is an infinite graph. The following are equivalent. The following are equivalent. I never remember how to say it. So it's G is transient. If a graph is transient, that means it has to have a flow going to infinity with finite energy. So there exists a theta from A to infinity. And A could be any vertex that I choose, right? If I have one vertex that has a flow with finite energy, then I could take another vertex and create the flow that goes to A, and from there it uses the flow from A. There exists a flow from A to infinity with the energy being finite, and that's it. Okay. So this is an approach that we will take many times. So we will use these things a lot, right? Because here we have ways of determining if a flow, ways of determining upper and lower bounds that we can always calculate over a flow. So we will give us ways to, if we want to prove that something is transient, we have to give an upper bound on the electric flow, right? Or of the resistance, right? So we will construct a flow and to see that it has low, and hope that it has low energy. And if we do that efficiently enough, we prove that the graph is transient. If we want to prove that the graph is recurrent, then we have to do the opposite thing. We have to construct a function, right, in order to show that the resistance is bounded from below. If the function has low energy, it will imply that the resistance is bigger than something, and that will imply that the graph is recurrent. Right? So let's see an electric proof to the fact that Z2 is recurrent. And if you will, I will say this proof hand waving, but you can see that what I'm going to use is an inequality due to Nash-Williams. It's theorem 2.42 in your notes. But that tells you, but it's a very intuitive theorem, so there's no need to, perhaps I will prove it to you next time. But what it says is that if you have a graph, if you have a network, or perhaps I'll just quote it. I have 5 more minutes. I'll just quote it without proving it to you. The proof in the notes does not use this exercise, but it uses another elementary. This is just an application of Cauchy-Schwarz. And what it says is that if you have a network A and Z, right, and you have, so here it is, and you have a sequence of cut sets. So a cut set is a sequence of edges. Let's say here, this is one. It's an edge such that if I erase all of them, then A and Z are separated. Right? So if I have 2 of them, right, or 3 of them, then it seems, right, it is very intuitive to think that if I have electricity flowing from A to Z, right, and I want to see, how bad can the energy be? Right? How small can it be? So how good can it be? So it's obvious that in order, if I take the unit current flow, so flow with the unit strength, if I have here 5 edges, it's clear that the best way that the electric flow could go is by giving 1/5 to all of these edges, right? And the worst thing that it could do from an energy perspective, right, from is give one edge the number 1 and all of these 0, right? So, and of course, when you have such a thing, you know, the worst case is 1 here and 0 everywhere, and the other case is all of them are equal. It stinks from Cauchy-Schwarz, right? This is so you want to prove that this is indeed the best case. So obviously there's a Cauchy-Schwarz there, and so what it says is that if I have a sequence of cut set gamma 1, gamma 2, gamma 3, and so forth, then the effective resistance between A and Z is at least the sum over the cut sets of 1 over the size of the cut set when these are unit resistances. Right? And when it is not unit resistances, then you have, instead of the size of the cut set, you sum the conductances over the edge of the cut set. So this is a very intuitive thing, right? Here you have to waste energy, which is 5 squared times 5, right? And here you have to waste, here I have 6, so it'll be 6 squared times 6. So you always get 1 over the size of the cut set. But this picture is a little bit misleading because the theorem, if it's drawn like this, it's very, when it's canonical, when it's interlaced, so this all cut set is contained in one of the parts of this cut set, then it really does work. But the theorem also deals with what if the cut set had like edges like this as well, perhaps, and things like this as well. So even if the cut sets are not canonical one after the other, the theorem still works, right? So this is a statement of what's called, this is the statement of Nash-Williams, and it's a very useful thing to prove recurrence of infinite graphs. So let's look at the example of Z2, just because this is what I promised in the beginning of the lecture. All right, Z2, here's our graph. Which cut sets will I choose to prove that it is recurrent? Right, I just choose, right, the cut sets will be, if this is the vertex A, I will choose firstly this set of edges, right, everything that intersects the purple, and the next I will choose this set of edges, right, and the next I will choose this set of edges, and so forth, right? This will be gamma 1, gamma 2, gamma 3, and so forth. And just by this, you can see that gamma n, the size of it is of order n, right? This is the theta notation, right? So this diverges, and we understand that the resistance from the point A to infinity is infinite, and hence Z2 is recurrent. And from what we learned, any subgraph of Z2 is also recurrent. And the nice exercise is to prove, not using this estimate, just by electricity, to prove that Z3 is transient. Okay? So in the next lecture, throughout this week, we will use the electric theory all the time, all together, except for the next lecture, which we will discuss only the circle packing theorem. But at the beginning of the lecture, perhaps I will provide some exercises, because I know if you've seen electric network for the first time in your life in this class, it could be confusing. I had to study it 3 times before I understood it. So some exercises are always good to make sure things are okay. But so I'll give them tomorrow, and tomorrow you do not have to think about electric networks except for the exercises. It could be a completely independent lecture. Thank you very much.